Alrighty, section 7.7 is called Exponential Growth and Decay. So our learning target today is to model exponential growth and decay. So that's what we're going to do. We're building off of our last section, which was about exponential functions, and we're specifically talking about what the difference between exponential growth and exponential decay is. So key vocabulary for today. Exponential growth, first of all. Exponential growth is a situation model with a function of the form y equals a times b to the x power, where a is greater than 0 and b is greater than 1. Okay? So for exponential growth, that has to be the case. So when we're talking about exponential growth, the growth factor is represented by the b, all right? And it would be 1 plus the percent rate of change for an exponential growth situation. So like, for instance, if it was 1.25, 1 plus the percent, so it would be 25% growth. Okay, if you're looking at it that way. That's just what it means. All right? We're going to talk about compound interest today. And when you get into the financial world or anything with stocks, stocks and bonds or um, savings accounts, you get interest on things. And compound interest is one of these types of interest, and it actually is an exponential thing. So compound interest is interest paid on both the principal and the interest that has already been paid. Meaning, if you owe money for some sort of loan, you owe the bank interest. They charge you interest on the money that you owe, and if it's compound interest, you also would owe interest on the interest. So as the interest grows, then you owe interest on that. So the faster you pay it off, the better in that case, because the less interest you have to pay. But anyway, we're going to look at that a little bit. And then the last thing we're going to look at is exponential decay. So that would be a situation modeled with a function in the form y equals a times b to the x power, where a is greater than 0, and b is between 0 and 1. Okay? So it's between 0 and 1. And that decay factor then is represented by the b, okay, again, but it's 1 minus the percent of change. So for instance, if b was 0.5, well, let's say b equals 0.6. 1 minus 0.6 equals 0.4, so that would mean it's a 40% decay. So whatever's taken off of that 1. So very similar to the growth factor. And we'll talk about those, especially when we do these examples. So let's start with exponential growth. All right? Exponential growth we just talked about can be modeled by the function a times b to the x, where both a and b are greater than 1. The b is the growth factor. So if we're looking at this like this, this is one way to look at it. But more specifically, I want to break it down into, and this is what the graph will look like again. It's growing. I want to look at it like this. The general equation for exponential growth would be, instead of a, we're using c. That's the initial amount. That's what you're starting with, or your starting point, your y-intercept. The 1 plus r, so that instead of saying b, it's just 1 plus r, so r is the rate of change, raised to the t power, and that would be over time, which is usually years. Okay, and that's explained right here. That's general exponential growth, because exponential growth does happen. It's stuff that happens over time. So here's an example. It says, in the year 2000, the United States had a population of about 280 million, and a growth rate of about 0.85% per year. So it says, write an equation to represent the population of the United States since the year 2000. So if we're going to say that, we're going to say y equals an initial amount, which is c, would be 280 million, times 1 plus, those are all zeros by the way, 1 plus the rate, which is, if you change that to a decimal, it'd be 0.001. 0.0085 because you have to move that decimal over 2 places back. All right, it's not 85%, it's 0.85%. And then raised to the t, so however many years. That's our formula that we're going to use. That's our equation. And then to number 2, it says, according to the equation, what will the population of the United States be in year 2010? So we're saying 10 years later. Okay, well, take that formula that we made, that function, and instead of t, actually, you know what? I'm going to do this. Instead of t, we're going to use 10 because we're doing 10 years. All right, and when you do that, I'm just going to say plug that into a calculator because that's going to be hard to do, especially with those big numbers. And you find out what the population will approximately be after 10 years. So what I'm going to do is I'm going to do that 1.0085 raised to the 10th power, and then multiply that by 280 million. And it's going to end up being, that's about 304,731,294. 304,731. 294. So I'm not going to round up because that would mean that we're adding like a half of a person. We're just going to leave it as how many whole people we have. But after 10 years, if it still at that very slow rate, because it's 0.85%, we'd have this many people in the United States in 2010. All right, and we can check the data to see if that actually worked out. I'm not sure if it did or not. But what I'd like you to do is try this on your own now. So it says, suppose that in 1985 there was 285 cell phone subscribers. So remember, that's your starting part in a small town. The number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were there in the small town in 1994? So 9 years later. So why don't you set that up, plug in for the missing parts, and see if you can figure out the number after that exponential growth. All right, so I just used the formula, plugged in the starting point, plugged in the rate, and plugged in the number of years, and I ended up getting 43,871 subscribers, cell phone subscribers. Now it does say, we have to put this back in perspective. That is a huge growth, but if you're growing that much each year, then yes, this would be correct. The problem, though, is, what if the city doesn't even have that many people? Okay, since it does say it's a small town. So that's where we could have some inaccuracies here. But on average, if it continued to grow like that, and there were enough people, that's what it would be up to after 9 years. Crazy how much things grow if it's exponentially. All right, let's look at this thing called compound interest now. Compound interest has to do with exponential growth. So you can use the following formula to find the balance of an account that earns compound interest. Very similar to what we just did, only one slight difference. So the number in front is going to be your P. That's still the initial. That's the starting. And then in the parentheses, it's 1 plus. Now this time it's going to be the annual rate divided by the number of times it does it each year. So we're adding that in there. And then T is still going to be the number of years. So the parts that are different are this N here and this N here. That's the difference between this and just a regular exponential growth. So here's an example. We're going to do an example. We're not going to spend a ton of time on this because I want to get to exponential decay yet. But it says, suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest. So by the way, 4.5% would be 0. If you move the decimal over twice, be 0.045. And if it says quarterly, that means it's 4 times per year. Okay? That is part of that formula. So what will our account balance be after she is 18 years old? So we know the $2,000 interest, we know the 4.5% or $2,000 principal, 4.5% interest. It's compounding quarterly. We needed to figure out her balance after 18 years. So I'm just going to use that formula. So if you plug in for the formula, I can plug in 2,000 for the principal, 0.045 for that rate. 4 is in for that because it's quarterly, and then 18 would be the number of years. So if we put that together, it would be this right here, and we simplify using a calculator. You'll end up with $4,485, sorry, $475.53 after 18 years. So without doing anything, just putting this money into this account, if it works out after 18 years, it would have over doubled. It's up to $4,475.43. Okay, by the time she um, is 18 years old. All right, so what I'd like you to do is try that one on your own then. It says, suppose the account in problem 2 pays interest monthly. First of all, what's the difference then? And what will the account balance be after 18 years? So if you want to pause it, go ahead and pause it. Otherwise, I'm going to work through it now. But we're going to say it's going to be 2,000, still 2,000, times 1 plus 0.045 divided by, now if it's monthly, that's 12 times per year. So we're putting 12 there now, and 12 times 18 here, all right, instead of 4. Now if we simplify that, it's 2,000 times 1 point, I did it on my calculator, so that would be 1.00375, and then 12 times 18, I think is 216, so that's going to be 216. So now if I do that, it's going to be, let's see, 1.00375 raised to the 216 power. Multiply that by 2,000. So, it didn't change it too much, but now it's at 44.89 and 1 cent. Whoops, 0.01, sorry. So if it's compounding monthly, that does change it a little bit. Not a ton in this case, but if it was a larger amount to begin with, it would definitely be a larger amount to end with. But we still are at the 44.89 and 1 cent. All right, so that is compound interest. And now the last thing I wanted to touch on was exponential decay. Very, very similar to exponential growth. The only slight difference is, and I'm going to show you, this is the graph looks a little bit different. The b value is always between 0 and 1. And I'm going to show you this way like we did before. Here we go. The general equation. So we're going to use this equation. Again, c is still the initial amount. That's where you start. R is still the rate, but in this case we're subtracting R from 1 instead of adding it, so it's that makes that number in the parentheses between 0 and 1. So this is still that rate, and t is still the time in years. Okay? So here's an example of how we can show that. During an economic recession, meaning the economy is going down, a charitable organization found that its donations dropped by 1.1% per year. Before the recessions, its donations were 390,000. Write an equation to represent the charity's donations since the beginning of the recession. So we don't know the amount of time right now, but we can put it into an equation. All right? So that equation we'll say is y equals the start, which is $3,900, times 1 minus the rate. So 1.1% would be 0.011. So if you move that 2 places over and you fill in the 0, that's where we got that. and raised to the, we don't know, so we're going to put t right there. Okay? Now it says estimate the amount of donations 5 years after the start of the recession. 5 years after the start. So we're going to make the time 5 years. So it's going to be y equals 390,000 times, it's going to be 0.989, I believe, raised to the fifth power. So calculator, I'm not going to do that in my head. Raise that to the fifth power and multiply it by 390,000. And I get 369,016. So 5 years later, if that recession continues, they're making that much less per year. That's over 20,000 less per year with their donations, which is kind of sad, but that's how exponential decay works. It goes down exponentially. All right. So what I want to end on is this one. So it says a student. I want you to figure this one out. It actually goes back to our exponential, our compound interest. See if you can figure out the error. It says a student deposits $500 into an account that earns 3.5% interest compounded quarterly. Describe and correct the student's error in calculating the account balance after 2 years. So I'm going to let you figure that one out. And as you do that, I want you to think about the learning target that we started with, to model exponential growth and decay. And we did do some extra stuff with compound interest in here. But determine whether you've met that goal, or you're almost going to meet that goal, or you are not even close to meeting that goal yet, and see where you need to go from here so that you can get to meeting that goal. All right? And by the way, the error for this last one was right here. They didn't change it to a decimal. 3.5% is actually 0.035. So that's what should be in there. All right? And that would totally change the answer. All right, that's all I have for you. So we'll see you next time.